Welcome to a lesson with Dr. Powell. Let's take a look at writing a vector function in terms of its tangential component and its normal component. So we're going to take this vector function, and in order to find this right here, recall this is the second derivative of the arc length function with respect to t, or arc length here. And another way of getting to this second derivative, so s double prime, is, well, first of all, s prime is equal to the length of the velocity vector, and it's in that direction. And so to take the s double prime, you just take the derivative of this. So of the velocity vector, the length of the velocity vector. So we have to find the length of the velocity vector, and then we take its derivative. So the length of the velocity vector is going to be a scalar function, just a number that would go here, well, as a function of t, but it's not going to be a vector. So these are going to be scalar multiples that are functions of t, but they're multiples nonetheless of these vectors in the t and the n. So to compute this, we simply take the derivative here. Oh no, not the derivative, the length of this. I mean the length of this first to get just a number. So it's 1 squared plus 4t squared plus 9 t to the fourth. Okay, so that is going to be the length, and that's going to be, this is s prime. So to find s double prime, which is precisely what goes right here, we end up getting just the derivative of this. This is to the 1/2 power, so we can think of this being raised to the negative 1/2 power, which I'll just write down as a square root down here. So it'll be 1, so 1 plus 4t squared plus 9t to the fourth. So raising, because I'm subtracting 1 in the exponent, so it drops down there. Then I have to multiply it by 1/2 out front, so that's like putting a 2 down there. And then but using the chain rule, I have to multiply with the derivative of the inside, which is 8t plus 36t cubed. So that is what s double prime is equal to. So that's exactly what goes here for the tangential component. Now, what about for the normal component? What would that be? Well, we could just use the Pythagorean theorem with this if we wanted to. But we have to but how do we do that? Now this plus this, and these are orthogonal to each other, equals that. So it's kind of a situation like this. And you already know what one of these lengths is. It's actually equal to this as a function of t. And you know what this is too, because it's just the acceleration itself. If you were to compute that, take another derivative. So you'd get 0 to 6t. Find that length, which would be the square root of 4 plus 36t squared. So if you take that and square it and subtract this whole thing squared and take a square root of that, you should end up getting this normal component here. But to make these things simple, why don't we just pick a value of t to work with for a minute to see what we can do here. For instance, what if t is what if t itself were equal to 1? So if t is equal to 1, then we can plug this in. We get 8 plus 36, which would be 44. So we get 44 divided by, and then we have 2 times square root of 1 plus 4 plus 9. So 15, 14, 2 root 14. Okay, and that's the tangential component. If we take that and square it and subtract it from this squared right here, with t being 1, so that would end up being 40, and take a square root, this quantity, when you work it out, will actually be, so at t is 1, that's actually the component of acceleration in that particular direction. Okay, now, another something else, another description of what this is right here is actually kappa times the velocity right here, so that length right there, squared. So since we already computed it like this, we could actually find kappa pretty easily. We know what this is squared, so this, right, so this squared, it was just be simply taking off the square root of this right here. So just be 1 plus 4t squared plus 9t to the 4th. But if you plug in 1 here at this particular time, it'll be the square root of 14. So, and then you square it, so just be 14. So 14 times kappa is actually going to be equal to this. So to find kappa now, all you have to do is take this quantity, I'm just going to call it A for now, and you divide it by 14, and wow, we just found the curvature is computationally. That's how you would proceed. Just a little thought. If you can split up acceleration into tangential and normal components in this way using the Pythagorean theorem, it's yet another nice way of computing your curvature. Thanks for watching.